today we will learn about modern recurrent neural nets. Initially, in the last week, we learned about vanilla recurrent neural nets that have many problems. Yeah, the well-known problems of recurrent neural nets is vanishing gradients, and that is actually solved by long short-term memory. So today we will spend time learning about modern recurrent neural nets. Nowadays, we don't use LSTM and GRU for language model, but usually we use transformer neural network to build a large language model. But it doesn't mean that there is no case we can still use LSTM and GRU. And in fact, the architecture of transformer is based on encoder-decoder architecture that is based on the previous architecture that we are usually use with the LSTM and GRU. So this is the summary of chapter 10 that I made for you. You have to read the chapter, not only take this lecture, because reading and experiencing the mathematical model is very important before you can do prompting using ChatGPT. So make sure that you read the chapter and you can implement some use case using ChatGPT, using LSTM and GRU and encoder-decoder architecture. Okay, let's start. So gated recurrent unit and GRU was born by different researchers, but they are solving a similar problem, which is they are solving the weakness of the vanilla RNN. So let's start with GRU first. So what happened with the RNN is sometimes it cannot memorize long sequence, and it cannot detect the pattern in short sequence. Okay. So the issue is because when we do recurrent neural nets, we just wire up the multi-layer perceptron, but we don't have state and gate. Yeah. So LSTM and GRU come with the new idea that instead of original vanilla, let's putting more gates and let's give the network some state, hidden state, so it can memorize short-term and long-term dependency in the sequence. Okay. So what happened after that? They propose architecture. So this architecture, you have to be able to read mathematically in the lower equation and also in terms of visual diagram in the upper picture here. Okay. So the sigma is a fully connected layers. You already learned about fully connected layer as a MLP, multi-layer perceptron, dense network, contain neurons, and weight parameters. Okay. So all of the sigma here, there is two sigma in GRU cell. So GRU come up with a cell that you have to compose to build your architecture. Each cell has input of hidden state of the previous cell and output another hidden cell, a hidden state H for the time t, and the input is hidden state H t-1. Okay, it's also input the sequence data X at the index t. So, but what happened compared to RNN, vanilla RNN, it has many gates, yeah. So as you can see here, there is a reset gate, update gate, okay? And all connected to weight parameters provided by fully connected layer with activation function, okay? You don't have to memorize this architecture, but you have to understand how it works if you come to see. So here, if you implement using PyTorch, PyTorch already provide GRU cell. Yeah, so don't worry about the implementation, but you have to understand how it works, how many gates, yeah, and what is the equation here is actually to explain the picture above, yeah. So hidden state is Z, there's an operator here, and multiply by the hidden state T minus 1, blah, blah, blah. Okay, you can connect these two pictures with the equation to understand more about the GRU. So in the chapter, GRU is explained after LSTM because actually LSTM has more gates, yeah. But here you can get the explanation, step-by-step explanation, first about the reset get, okay? And then the computation, how to compute the reset get output and update gate output, R and Z, yeah? All will be connected to the neural network parameters, which is W. Tensor W is a fully connected layer and activation function. And then there is a candidate of the states and then hidden states, yeah, and then summarized in the slide like this, okay? Okay, you don't have to memorize this. Just make sure that when you create the code using PyTorch and then you create GRU code cell, means that you are implementing this complex cell with gates and inputs and also weight parameters of the fully connected layers. Okay, so long short-term memory also handle the same problem, yeah, because vanilla RNN cannot preserve short and long-term input, okay, and also sometimes vanishing the gradient during the training. So that's a big problem because the network is not stable. So what is the difference between GRU and LSTM is actually on the number of gates, yeah, okay, and the number of states, yeah. So here, not only hidden states, LSTM has a memory cell, okay, and it operating memory cell and hidden state. It has 3 fully connected layers, as you can see here, sigma. It has more gates, yeah, forget gates, input gates, output gates, and it has candidate of the memory, and it has memory cell. So if you compare GRU and LSTM, GRU is actually simplified version of LSTM. Sometimes LSTM is better, sometimes GRU is better, depend to the patterns inside your sequence data, okay? So people use GRU and LSTM comparable. Sometimes they use both and they see which one is performing better and they choose that one because there is no theory that can explain LSTM is better than GRU or GRU is better than LSTM. So we do heuristic experiment. If the model, LSTM model perform better, then we use LSTM, okay? Long time back, before the time of transformer, we implement name entity recognition, we implement machine translation, all of the downstream NLP tasks using LSTM and GRU with more architecture. But now, most of the downstream tasks in NLP is replaced by language model. But still, if you are working with small computation devices, like for example, you are developing keyboard for Samsung mobile phone, sometimes we use LSTM to predict what is the next key that you touch in the keyboard in the mobile phone that utilize LSTM or GRU. Okay. So after we know that the RNN is not stable, then we use GRU and LSTM, and then some architecture coming. Some people make deep recurrent neural network by stacking the network, the hidden state, yeah? So instead of they're making it as a cell with gates, the RNN say, what about just make a hidden state, okay? And just stack the hidden state. This architecture was not better compared to LSTM, stacking LSTM and GRU, but historically, some people propose this kind of architecture, including the bidirectional RNN, yeah, to make a language model or to predict the missing word in the syntax sentence and many more. Also, people use dynamic programming in Markov model, and they solve it using uh, a stack of the hidden state. Some people also make bidirectional model, like they're stacking the hidden state in bidirectional way and utilize dynamic programming in Markov, but it's rarely found now. So if you back to the history, most of the people are actually stacking LSTM or GRU instead of doing this kind of things. So machine translation, name entity recognition, sentiment analysis, all of the downstream of the natural language processing was usually implemented as LSTM and GRU. You can try ChatGPT to make, for example, simple name entity recognition or simple machine translation later on during the practice session with JC, yeah. But that kind of code is everywhere in GitHub. So let's say I say make synthetic corpus in Bahasa Indonesia and English, yeah, and then write Python code, or you can more specific on PyTorch to implement machine translation using LSTM and evaluate the result. Okay, so this kind of typical codes using LSTM, long time back, you can find many in GitHub. Yeah, so let's say you have a corpus in Bahasa Indonesia. Saya suka makan nasi, dia pergi ke sekolah, blah, 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 and English target. And then you say from this sequence of words, there is a patterns that map to the sequence of words in English. And you want to implement machine translation using LSTM. So how LSTM works on that? It tokenizes it. It tokenizes the corpus using some embedding. Okay. So, and then create the vocab, and then make this model, yeah. In this implementation, it uses encoder using LSTM and decoder using LSTM. Why it uses encoder-decoder architecture? Because machine translation usually require not only simple classification, but it has input, two input of corpus, the input of original sequence and the target sequence of English corpus, okay? And then it trains this architecture. That's why in this chapter, they also introduce encoder-decoder architecture, okay? This architecture is utilized by many language models now. But instead of implementing this architecture encoder-decoder using the LSTM and GRU, the modern neural networks now utilizing transformer block. And they can compose many transformer block up to trillion parameters, make a very large model, language model for machine translation, and all of the other NLP tasks into one model. Long time back, we implement machine translation by using specific encoder-decoder. If we want to do sentiment analysis, we implement another encoder-decoder. If we want to have neural entity recognition, name entity recognition, then we make another architecture. So using language model, all of those downstream tasks can be implemented in one very large model using transformer. Okay, so now we learn about the encoder-decoder architecture. Let's say for machine translation, you put the input into the encoder. The encoder is actually can be LSTM or GRU. And then the output of encoder is the hidden state of or the latent variables of the input corpus. And then the decoder will have to reconstruct based on the hidden state or latent space into the target English words. Okay? So this is what we call sequence-to-sequence learning with encoder-decoder architecture. So you input the data corpus, like let's say here English to France, they are watching, and then you input, you train the parameters of the encoder LSTM, and then you train the parameter of decoder LSTM. So this is, the input is in English, the output is in, let's say, I don't know what is this, but should be France, okay? So once you have enough corpus, then these network parameters will stabilize, converge, and then you have an encoder-decoder. If you give new data in English, it gives you output in France, okay? So it's very common at that time. We implement machine translation using LSTM encoder-decoder or GRU encoder-decoder, like the code that I showed you before. Okay, so by the end of this chapter, I hope you can implement basic NLP tasks like name entity recognition, sentiment analysis, let's say machine translation. Even you can do language model using encoder-decoder. Okay, so you can expand this prompt. Let's say you want to make name entity recognition. Yeah, so name entity recognition is not translation, so you have to just make synthetic corpus in English. Yeah, and then write Python codes to implement name entity recognition. Using LSTM and evaluate the result. So name entity recognition is actually a recognition task like classification. You have to classify whether the words is actually entity or not. Yeah, means that you have to annotate your corpus and then let the LSTM network make your name entity recognition. Okay, so NER usually implemented as a LSTM for recognition or for classification. Using similar prompt, you can also prompt, let's say, write Python code to implement sentiment analysis. Sentiment classification. Okay, let's say in Bahasa Indonesia. So this is a very simple corpus, and then it will give you sentiment analysis. But of course, sentiment analysis is a classification that requires some annotated labels, what kind of sentiment from this corpus or sentence. Okay. You can also use the same, make synthetic corpus in English, write Python code to implement language model. Remember, language model is a probability engine that can predict the join probability of words. Yeah, it compute the join probability of words given a corpus. So you can implement simple language model using LSTM as well. Okay, this is the sentence corpus that give, and then implement LSTM for language model. Okay, so all of these tasks is a very common NLP task that we usually implement using RNN a few time back. Yeah, not very long time. In 2020, we still use LSTM, GRU, encoder decoder. But suddenly, after the large language model, all of these downstream tasks is replaced by large language model because they have the whole capability. They are trained by very large corpus, very large annotated corpus, and it already contains many downstream tasks. So currently, we much more moving toward large language model to implement NLP. Instead of we train from scratch, we utilize existing language model like GPT 3.5 here, or Gemini, or Palm from Google, or Apple also released, or Grok from Tesla. So in the future, there is a lot of LLM that you can manipulate, you can program, you can make your application, natural language application, using pre-trained LLM that you consume. Okay. So, but long time back, we implement this kind of NLP tasks using different architecture. Okay. So this chapter is very important for historical reason that not so long time back, we still doing this specific architecture for specific downstream tasks. Yeah. But now, because we can have attention and transformer, which is we will learn about attention and transformer next week. Now it's already replaced by large language model, so people are much more moving towards the large language model. But it doesn't mean that LSTM and GRU is dead, or we didn't stop using LSTM and GRU, because there is any case, let's say you are implementing the next word prediction of keyboard in Samsung mobile device, or you are implementing simple sentiment analysis for your business. Sometimes it's too costly to utilize large language model. Okay, but that case, I think, slowly will gone because large language model have more capability. Okay, so for example, keyboard, maybe we don't have to utilize implement embedded LSTM anymore in keyboard in mobile phone. We just call API from large language model. Okay. So that's it for today from me. I hope you learn. You can learn in terms of fundamental, conceptual, and practical. You balance F, C, and P, because expertise is a product of FCP. If you too much on practical, you are not scientists. Okay, maybe you are engineers, or maybe not even engineers. Yeah. But if you can learn the mathematics in this book, yeah, the mathematics is not hard anyway. So it's just like making architecture from the fully connected layers with some algebra tensor operation. It's not hard. Yeah. So if you can learn the fundamental mathematics, you have the intuition to know what happened with your network during the training. You can have intuition to improve. Let's say you can improve regularization, you can improve objective function using mathematical distance. You can improve many things if you understand the fundamental. If you understand the conceptual, you can make modification, further modification of the architecture you can create more abstraction on top of your network. If you only know practical, you just know the coding part, the codes, but nothing you can do to improve accuracy, to improve the model itself. So it's very limited. So I hope you can learn FCP way, fundamental, conceptual, and practical, and then improving along the way during your journey in master degree or your journey as a professional AI engineer after graduate. Okay, I stop here. Is there any question before I give to Jesse for prompt engineering using ChatGPT? Okay, if no question, then we'll continue with practical session. Please, Jesse, continue the session.
Yes, thank you. Let me share my screen first. In fact, okay. Hello everyone, welcome to the practical session of this course. And today we will try to practice with modern RNN with GRU and LSTM like we did last week. But for this session, we are going to use it for simple sentiment analysis or sentiment classification. So I hope everyone can open their Google Colab and ChatGPT so we can do this together. And for our first prompt, we will ask ChatGPT to give us a simple Python list dataset to be used for sentiment analysis. So and just go up to ChatGPT and can immediately ask to write a simple Python list with what do you call it? List dataset. With sentences and the corresponding sentiment. Let's see. Okay. This is the result. Let me copy this prompt so everyone can do it with me. I've already sent the prompt. Let's copy this code and let's run it. For this one is only short sentences and their corresponding sentiments. For RNN, we first have to what's it called tokenize the text. So we can ask ChatGPT tokenize the sentences dataset. See, they are using NLTK to tokenize the words. Let's see. So tokenization is one of the crucial steps to do any training. So let me tokenize dataset and the sentence and let me see. So this is not the tokenize we want. We want to tokenize so each of these words like I and movie has a corresponding an ID for each of them. Let me Let me see if refreshing the regenerating the prompt will give us the right code. Oh, it's still using the same code. Let me see if I can edit the prompt, tokenize the sentence data set. So it has a unique ID number. Let me see. Okay. Let me copy this part. Oh, this is only tokenize the sentences. Let me see. Actually, there is another uh, library to tokenize with TensorFlow tokenizer as ability to use the set using the specific library, so we can have for the same result for everyone. Uh, Let me try to run this first to extract the sentences and try to run it. Oh, I haven't imported the library. One sec. Okay. For this one, it's already tokenized. Like, for example, in sentence 2, we have the word D. And the same with on the sentence, the fourth sentence, we have also D with the same ID or number. Also the same with I, with the corresponding number is 3, and so on. This is the tokenized version of our dataset. Okay. After we have the tokenized version of our dataset, we can continue our next step to train this model. Step is to pad our sequences so it can have the same length for each dataset of for each row. Let me to let me write an Excel. Let me type this first. An Excel to pad the sequences. And oh, let's see if I have copied the prompt first to the chat to tokenize, and after that to pad the sequences. This is the code that was run it. For this one, we have max length of 20. I hope it's enough. Let me see. Let's see if it's all right. This is almost the same, but each of these sentences are padded to so it have the same length of 20. Maybe for this one, we can adjust it, the maximum length for our use. If we have longer sentences, we can set the max length of larger number to accommodate our all of our text. Also for this one, we tokenize the sentences with words instead of we can also tokenize the sentences with uh, the characters like the alphabets or the punctuation and then so on. But this one we are going to tokenize this dataset with each text. I mean each word. All right. So I'm sorry. Uh, for this one, after if we have padded the dataset, for the next step we can train the dataset with our model, which is we're going to use LSTM to train the dataset and see the accuracy. Can ask GPT to write a new cell to train the dataset with LSTM and see accuracy. For this one, we are only using such a small dataset, so we can expect it to be uh, good for production or using a regular use. So, but I hope it can show the basic usage for implementation of these specific models. Let me see. Sorry, this one. All right. What it's going to do is setting the labels. One, if the labels for sentiment is positive, or zero if the sample is negative. So what is called is one-hot encoding, basically changing some type of what is called columns on this dataset to a number, so we can train it. For this one, positive is 1, while negative is 0. If it have many more sentiment, like maybe sad or angry, you can change the numbers to 0 to maybe 4, corresponding to how many sentiment we have. For this one, defining the model with embedding STM64 and dense of 1. Let's run it. It has 10 epochs. See, oh, for this one, it has quite a good accuracy with 80%. Let's see if we can try to test the model with a new sentences. We go back to this tab and ask write a new cell to test or train it model with a new sentences. Let's see, favorite sentence. Oh, very good. Oh, sentences, because I said sentences. And oh, let me copy our prompt first to the chat. After path sequences, training the dataset with LSTM, and the last one is for the new cell to test or train it model with new sentences. It should not be here. Okay, so there is that for trained model and for the prompts. And let's see our models with new sentences. We have these 5 new sentences, and let's see. Enjoyed the concert last night. As positive is true. Terrible is negative is true. The weather is amazing is true. My expectation is positive. Disappointed is all right. This one is should be negative because the sentence is disappointed for this product. So to write to have a better model, obviously we have to have better data sets. This one is for LSTM, and the next one, let's see if we can continue to using GRU. It should be the same for training, with difference in the defining the model for our GRU model. Let's see. We can ask in this tab to write a new cell. In here, we are using prompting write a new cell, not a Python code for each step, so it doesn't return a whole new code, one whole code, so it can give codes in cells. Write a new cell to train the set with GRU instead. Let's see. They're using GRU embedding. Sorry, with 10 epochs and batch size of 16. Ah, see. This code will put under here and run it. Okay, this one is actually not better than the LSTM one. While it has 50% of accuracy with GRU, maybe we can also edit this the hyperparameters like epochs and batch size. Wow, and validation split. The validation split is splitting the training model, so the 20% of our training model is used to evaluate or test our model. See if we can try with new sentences also. For easy to use, we can ask GPT to make it a function instead. Write a new cell to get a function that accepts new sentence, and output the predicted, let's call it the predicted sentiments. Okay, using the new model or GRU model, I think it's going to be better. Okay, as you can see, is showing the predicted is wrong because maybe it reflected from the accuracy of this model, which is only 50%. So maybe you can do part of these models with LSTM and GRU and find your best fit for your dataset, your provided dataset. For this one, maybe for a specific dataset, it's better to use LSTM other than GRU. So you can test it yourself, which is the better on performance or on the result or the accuracy. On this one, we are only using the small dataset of pre-made generated from GPT, and maybe we can ask GPT to use a larger dataset Uh, so it can maybe gives off a better result and uh, accept more new sentences. On this one, I enjoyed the party last night. Let's see. Mm, as GPT-2 uh, in yourself to train with STM model, but uh, with much larger data set. They're just going to give off um, larger data set with it with generated, but in in practice, you can also search for data sets like this one. What's it called? Let me see. Twitter dataset for sentiment analysis, and there are many datasets you can use, like from Kaggle and Hugging Face. Let's see. I have actually opened this dataset with sentiment analysis for from Twitter post. This user scrapes Twitter websites and see the content and probably labeling this contents one by one. Let me see. Let me see on the overview. This is entity level sentiment analysis for Twitter. Given a message and an entity, the task is to judge the sentiment of the message about the entity. Let's see. On this one, it has tweet ID, the borderlands are, I mean the entity, which is like Microsoft, concurrency Rainbow Six, Borderlands, and this is the sentiment. It has positive, negative, neutral. Uh, let's see, and the actual tweet content. For this one, maybe we do not really want to um, use the entity. Maybe we want only just uh, to classify the sentiment of the tweet content. Let's see if we can use this uh, sentiment analysis data set. One set data. So if we have here, uh, let me see the data set, the zip file, and the train CSV. Let's see. Okay. So one sec. Um, we can just for this one we don't have to. We can just create a new notebook. Oh, my bad. We can just create a new notebook and copy, upload our dataset to the file system on this. See, let's upload the files. Forgot. Ah, this one. You can just drag and drop to, it's not that big, only 10 megabytes. I hope it's uploaded fast enough. All right. While we wait, we can ask GPT. So we give him some context for our dataset we are going to use. I have a Twitter dataset filled with these columns. You see, what are the columns? With ID. Let me see the CSV file. Oh, with the first columns is Twitter ID, and the second one is entity, and the sentiment. Also, the last thing is content. Want to edit from content slash, let's see, content, this is content slash Twitter underscore training, Twitter underscore training dot CSV. And open it with pandas. See, it gave us the code. Right. This is Twitter ID, entity, sentiment, and content. First, let me see. Let me copy this prompt, and let's create a new prompt. Sorry. Let's see. I just want the sentiment and the content. I don't want the ID entity. Remove the Twitter ID and entity column. Like this is part of the code, and let's run it. All right. Is remove the columns, and the next thing we want to clean our dataset. So if it has empty rows or empty values, we want it just be removed. Remove empty, wait, rows with empty values, and do cleaning on the data. See, we copy this prompt. Sorry, and remove rows. Okay. They're cleaning the text of converting the text is to lowercase, remove non-alphanumeric like dots and punctuation marks, and tokenize, and removing stop words. Let's see if this code is working. Let's run it. Okay, they're using LLVK again. Sorry. While we wait, maybe they're cleaning a bunch of data. So for this one, it has quite rows. So around 75,000 rows of data. Okay, that's already done. For this one is I'm getting border and border. Let's see if it's going to better on training the sentiment analysis. So on the cleaned dataset, you wait, train a LSTM model to see the sentiment for each content. Let's check the code they're giving us. All right, they're encoding the labels like before and splitting the train and test dataset. And let's see if it's going to be a good model. Okay, I forgot to import let me import. My bad. One sec. Oh, this one. See, it's going to train, but maybe for this one, it might take some time, but you can always make it better with runtime type of GPU run type. Right, this one might take longer than we thought. Only 5 epochs, but this might take some time. But I hope everyone can do it the same on after this class with training models. Maybe if you have already done the Twitter, maybe you can just search another one other than Twitter's, maybe Corpus, and also check the sentiment analysis. And after that, maybe you can also do a bunch more later, like translation or text generation, and many more uh, usage of these models like LSTM and GRU, and do it on much wider range of data sets you can use. Okay, this one is maybe taking too long. Thank you everyone. Maybe that's all for today. I hope everyone can do it on their meantime. All right. Thank you everyone.